Welcome back. In this class we are going to discuss about an important topic, that is estimation of Cmos inverter delay. This is a very important topic for your external point of view, or it can also be called as derivation of rise time and fall time. Rise time and fall time. Is it okay? Then you have to remember these two names. In the external point of view, they will ask either estimation of Cmos inverter delay or derive rise time and fall time. Is it okay? Now first of all, we are going to assume that we are having a Cmos inverter. Okay, the load capacitor is going to be charged or discharged depending upon the input given. Then the charging innocence we have to determine the rise time. Okay, discharging innocence we have to determine the fall time. Okay, now we are going to analyze this estimation of Cmos inverter delay in saturation region. If you observe that, we know that in the saturation region, okay, the drain to source current is equals to beta into VGS minus VT whole square divided by 2. Is it okay? Now here you can observe that here we required a saturation of P and a saturation of N. First of all, this is a general expression you have to remember, and we will see the analysis depending upon the figure. Is it okay? Now you can observe this. This is a rise time model I have considered. You know very well that when input is applied 0 for a Cmos inverter, you know this one. This is your Cmos inverter, right? This is your input. This is a load capacitor you are having. Okay, now you can observe that when input is 0, that means the transition is from 1 to 0 transition. You can observe the transition is 1 to 0 transition. That means the input is 0. Then PMOS transistor will be turns on and NMOS transistor will be turns off. I hope that are clear. Then you can observe very clearly from this point of view. Since PMOS transistor is turns on, I am considering this is in saturation region. Therefore, there is a flow of current, and NMOS transistor will be turns off. Therefore, it will be act as an open circuit. Is it clear? Therefore, the supply will flow and the capacitor will be charges. Is it clear, all of you? This is a rise time model. Why? Because here if the input is 0, since the PMOS transistor is turns on and NMOS transistor is turns off, the current flows and the capacitor will charge. Is it okay? Now we have to determine how much time the capacitor will take to charge. That is an important point we have to talk about. And here I am considering, you can observe very carefully, you can observe this expression. Okay, now will you please tell me what is the basic expression? Just now I said that, okay, IDS, but here I am going to talk about P. That means I am going to talk about PMOS beta into, but I am going to talk about beta P, that is PMOS VGS minus VT. But we know that for a PMOS transistor, the threshold voltage is a -1. Therefore, I am considering magnitude VTP square divided by 2. I hope that are clear. This is square. Okay, this is our expression. Now you can observe very carefully here for this expression. Okay, now you can observe that I need to find out the voltage at this capacitance. Can anybody try to tell what is the voltage across the capacitance? V is equals to 1 by C integral I into dt. I hope that are clear. Now what is V? V out. What is C? CL. What is I? That is DSP. I hope that are clear. You know very well that this is a constant current because it is in saturation region. Therefore, it will be IDSP divided by CL. Then integral into dt becomes what? T. This is your V out. I hope that are clear. Now based on this expression, if somebody asks you what is T for you, then tell me T is equals to absolutely V out into CL divided by IDSP. Is it clear, all of you? Now you know very well what is IDSP. Beta P into VGS minus magnitude of VTP whole square divided by 2. Okay, that is the expression I am going to write here. This one. Okay, now you know very well that just now we derived T is equals to V out into CL divided by IDSP. Since IDSP is equals to beta P into VGS minus magnitude of VTP whole square divided by 2. After substituting this here, you may get this expression. I hope that are clear. Now let us assume that V out is equals to plus VDD. Okay, the value of V out is plus VDD, and you can observe very carefully T is equals to rise time, and the threshold voltage I am considering 0.2 VDD. Okay, that means you can observe these three values. I am considering T as a rise time, output voltage as a VDD, and the threshold voltage as a 0.2 VDD. Therefore 2 into V out becomes VDD into CL divided by beta P. What is VGS? You know very well. VGS is equals to VG minus VS. This is connected to VDD and this is connected to 0. Therefore VGS becomes VDD. I hope that are clear, all of you. Now I am substituting in this place of VGS, I am substituting VDD. Now you can observe very carefully. VDD minus, what is VTP? You know very well, 0.2 VDD. Is it clear or not? Is it understood? What is meant by 0.2? Don't forget you are having a square here. 0.2 VDD. Okay. Then after substituting this square, 0.2 VDD, okay, you may get 0.2 into 0.2. Then what is the value of that? 2 2's 4, then 0, then hyphen, then 0 0, 4 0 0, then 0.04 VDD square. 0.04 VDD square. Are you clear? After taking this VDD, it becomes what? Beta P into 1 minus 0.04. I hope that are clear. The numerator won't change. Okay, then approximately after doing this calculation, the rise time will be what? 3 into CL divided by beta P into VDD. Okay, and similarly we have to do the same thing for fall time model. You can consider this one. When the input is now 1, okay, just recall the Cmos inverter you are having. This is VDD, this is VSS, this is a load capacitor. This is a load capacitor. When the input connected to the gate is 1, then it will be in off condition, it will be in on condition. Therefore let us assume it is in saturation, then the capacitor will discharge. Okay, then therefore this is the fall time model you can observe. Similarly, if you do the same expressions, if you consider IDSN. If you calculate the output voltage, okay, if you assume T as a fault time, now here V out is 0. Okay, if you assume the same, then you can get the same expression. Okay, 3CL by beta n into VDD. Okay, now you can observe that very clearly. That is a very important point. If you take tau R by tau F, that means if you consider the relationship between rise time and fall time, if you consider the relationship between rise time and fall time, what is tau R? Absolutely 3CL into beta P into VDD divided by 3CL into beta n into VDD. You can observe very clearly VDD, 3CL gets cancelled. Then this beta n will come upside and beta P will be downside. Is it clear? Therefore, this is our expression. But we know very well that, okay, we know very well that you can observe un is equals to 2.5 times mu p. Therefore, beta n is also equals to 2.5 times beta p. Now after substituting this here, this becomes 2.5 times beta p divided by beta p. Beta p gets cancelled. The value becomes 2.5. Therefore, this is equals to 2.5. Finally, we can conclude that the rise time is 2.5 times the fall time. That means rise time is slower than the fall time. How much slower? 2.5 times slower. I hope that are you clear. And you can observe based on this expression, tau R is equals to, you are having one expression, that is tau R is equals to 3CL by beta P into VDD. That means, and similarly tau F is equals to 3CL by beta n into VDD. That means either rise time or fall time are directly proportional to load capacitance, and inversely proportional to VDD. I hope that are you clear. This is a summary about that. You can consider this one. Okay. Finally, this is the main thing you have to observe. You can observe that very carefully. The rise time and fall time are inversely proportional to VDD, directly proportional to load capacitance, and the rise time is slower than the fall time. Is it clear? That's it for today's class. If you are having any queries, please comment. Thank you very much. Have a nice day.